Hello there. Today, we're going to discuss PAXOS and RAFT. In order to fully define, understand, and contrast these two, we need to define what are consensus algorithms. What are consensus algorithms? In distributed systems, there are multiple components. Some, if not most of these components, perform work simultaneously. It is ideal for these components to agree on a single data or decision. For that to happen consistently, consensus algorithms are used to make sure that all these components are in agreement. Therefore, they must be reliable. Consensus algorithms must also be fault-tolerant. That means these algorithms must allow each system to reach a consensus despite the existence of failure in one or more of these components. Both PAXOS and RAFT are consensus algorithms. They both let one of the components become a leader. The leader is responsible for telling other components what decision it would like to have a consensus on. PAXOS and RAFT, multiple instances of the algorithm can be run. In each instance, the same or different component can function as a leader. How many instances can the algorithm run would depend on the capability of the machine that it's on. This follows the concept of parallelism within each system. For the PAXOS leader assignment, the algorithm assigns the leader less systematically. It can choose a component with the highest or the lowest rank at the time of selection to be the leader, and it may not necessarily be the best decision. In PAXOS, any component can be the leader. The process may be simple, but PAXOS requires there be a space between instances of the algorithm, which usually dependent on the maximum number of components. The leader of a new PAXOS instance also needs time to learn about the previous instance before it can make a decision. This can make system suboptimal or inefficient. In RAFT, there are restrictions on who can become a leader. Only the most up-to-date component can become a leader. That means that those components already have sufficient knowledge from the previous instance and that a learning process may not be necessary. This process can make the system more efficient. The qualified components may be one or more, and anyone can become the leader. In RAFT, qualified components will send a leader request to other components and waits for a reply that this is a confirmation that it has been selected as a leader. If it doesn't receive a reply, or it may receive a message that it has not been chosen, it will move on and accept the decision of the other components. Distributed systems do not always perform in sync, and between components and between instances. With this in mind, failures and election of leaders can occur at different times. This can cause confusion for the whole system. Components can send messages to others who are in a different instance. If a component receives a message from an old instance, they must reject that message. If a component receives a message from the current instance, it can accept it. If it receives a message from a newer instance, it must follow that and accept the commands coming from the newer instance. Commands sent from the leader must contain a record from the previous instance, and receivers must confirm this. Receiving an incomplete message or a record can confuse receivers, which will make arriving to a consensus longer and perhaps impossible. In PAXOS, the leader is not always guaranteed to know everything, so it leaves a learning phase to learn everything about the previous instance before it can send a message to the other components. In RAFT, the leader doesn't need a learning process. It already knows all the details from the previous instance, so it can move on to message sending as soon as it's chosen as the leader. Here's the summary of today's discussion. Thank you for listening.